presentation in a series of 6 one-hour presentations on pharmacogenomics. Beth Newman, pharmacy resident, will present all 6 lectures. Beth is a graduate from the Purdue University School of Pharmacy. When she came here as a resident, she said she'd like to do something in pharmacogenomics as her annual project. We don't have much going on, so education was one of the things that were available to us. That being said, her project is to study the change in knowledge over time of a group. The group is sitting up front. They've been given a device that will allow them to answer questions that are put on the screen. They'll answer anonymously, but as a group, we will assess on knowledge and the change in that knowledge over time. So here's how it works. When a question appears on the screen, notice the clock in the upper right-hand corner is set at 30. When it starts to spin, it'll count down to 0. You can answer after it starts to spin and before it gets to 0. Don't answer before it spins, and if you answer after it gets to 0, your answer will not be included. Because we're looking at the change in knowledge of this group, it's important that the group be consistent, and I appreciate the commitments you've made to attend all 6 lectures. This is from last week's Nature magazine. I just want to read the last 2 sentences. As the evidence builds, the use of pharmacogenetics may well become a common sight in hospitals and pharmacies around the world. But medicine is inherently conservative, and the solid data are required if clinical practice is to change. Beth, what is that evidence?
Thank you, Dave. Thank you for that wonderful introduction, Dave. No? How about now? Hello, hello? There we go. Perfect. And thank you to all of you for agreeing to come to all of my lectures. I really appreciate it. And so, without further ado, we'll cover today an introduction to pharmacogenomics. So hopefully after we finish in 1 hour, you'll have a better understanding of what exactly is pharmacogenomics, as well as how to apply some of these concepts to the practice setting, whether it be just recognizing which drugs are affected by genes, and how to interpret and act on genetic test results that may become available here. All right, so adverse drug reactions are very prevalent, as we all know. There are about 2 million serious adverse drug reactions every year reported to the FDA, and they were considered to be the 4th leading cause of death in the U.S. in the year 2000. About $136 billion are spent annually just in the U.S. on adverse drug reactions. And of the 27 drugs most frequently associated with adverse drug events, 59% of these are metabolized by an enzyme known to have genetic variations related to poor metabolism. So that is how the pharmacogenomics ties into the prevalence of adverse drug reactions. And so there's a couple of opportunities for pharmacogenomics here. About 1/4 of patients take at least one medication that in the labeling has pharmacogenetic information as required by the FDA. And within the Monroe Clinic, of the 300 or so patients that take more than 20 medications, 30% of these take at least one medication that is metabolized by an enzyme called CYP2C19, and 10% of these patients take medication that's metabolized by an enzyme called CYP2D6. So that's a significant portion of our patient population that can be affected by. And this is a slide that kind of shows the prevalence of high-risk genotypes within the population. So on the last slide we mentioned CYP2C19, about 50% of the population has a high risk. We'll get to what that means in a second. variation of that gene. And so as you can see, it's would initially think high-risk genomes. All right, so now we'll go into the pre-assessment mode. Everyone who's in the study, get out your clickers. If you're not in the study, feel free to write down on your sheets. And we will hit the start button. Now, what is pharmacogenomics? A, how medications affect the genome. B, how differences in individual genomes affect responses to medications. C, research that uses genomics to discover new drugs. D, how proteins turn genes on and off. Or E, I don't know. More seconds. All right. Next question. What does the star in CYP2D6 star 2 indicate? A, a gene. B, a diplotype. C, an allele. C, a protein. D, an allele. Or E, I have no idea. Which of the following is not a good resource to find pharmacogenomic information? A, ABCD. B, CPIC. C, PharmGKB. D, FDA labels. Or E, DPWG. Not on this one. Which of the following is not true of CYP2D6? A, possible variations include both copy number variations and single nucleotide polymorphisms. B, copy number variations always result in increased enzymatic function. C, it codes for a protein that metabolizes codeine. D, it has over 100 possible variations. Or E, I really don't know. Which of the following is true about tramadol? A, one of its metabolites is a much more potent opioid agonist than tramadol itself. B, it's metabolized by CYP2C19. C, poor metabolizers should have their dose decreased by 30%. D, codeine is an acceptable replacement for patients with CYP2D6 variations. Or E, I give up. Let's make this end already. All right, and that was the end. Congratulations, you made it through the pre-assessment. We won't go out. We'll do that after you know things at the end. So why do patients react differently to medications? There's a huge number of variables that we take into account and that affect variation. There's the environment, lifestyle. If you think of a patient with a sedentary lifestyle, they require different kinds of medications, or diabetics, or we'll come to that. Age, we won't give a child the same dose as we would give an adult. Gender, we alter doses based on gender a lot. We do weight-based dosing. Comorbidities, if you think the patient has renal failure, you wouldn't dose medications in the same manner or give the same medications. And then genetics is another factor that can play into this. So it's one slice of this pie. Epigenetics is another factor, but we won't go into that during this lecture series. It's a little bit beyond the scope here. And then there may even be more factors that we don't know about. So zooming in on that genetic slice of this variation pie, this is pharmacogenomics. Pharmacogenomics is how variations in patients' genetics impact their variability in drug response, whether it be an increased effect or decreased effect. And this is kind of summarized in this picture. If you look over at, over here, you have 3 patients, and this is kind of resembles a section of their genome. So this blue guy has a normal, quote unquote, genome. The yellow guy has one base pair that's different from the blue man. That would be considered a polymorphism. So kind of think of it as a mutation, but technically mutation only occurs in less than 1% of the population. So polymorphism. The red guy has a different polymorphism, so also one very similar to the blue, but one slight difference, the G from the T. So if you mix all these people up into the population, you don't know who's who right away, and you give them all the same drug treatment, odds are most of them will have good, effective care. But there will be a subset of them that don't get as much effectiveness as you would normally expect, and that they all have the same different aspect of the genome. And then you might have another subsection of this population that experiences increased effect, and to the point where they have side effects. And so that would be represented, all the patients here have that other polymorphism. So that is the basic idea of pharmacogenomics. There are different types of genetic variation that this can fall under. The most common one is usually the single nucleotide polymorphism, abbreviated as SNP. So if you hear SNP, that's what it's referring to. And that is, as we saw in the previous slide, just the one base pair change. It's substituted for A, G, C, T in that one position. Copy number variation, or CNV, is another type of variation. And that occurs when the gene is duplicated. The entire gene is just there twice on the genome. So if you look at this image right here, if you consider this big one up here to be the normal chromosome, down here you see there are two B genes in a row. That would be an example of copy number variation. And so if you think, if you have two genes in a row and they're both transcribed and translated, then you'll have twice as much protein produced at the end. Another type of genetic variation is the short tandem repeat, and that is when just this little section is copied over and over again. You can see that down here where they have the B gene and then a little bit of the B gene multiple times. Another type on the small level could be insertion or deletion. So if you have a row of base pairs, A, G, C, etc., and the G is taken out, that would be a deletion. Or if you insert an extra, whichever base pair you would like, that's an insertion. And if you think back to, I don't know, high school, college, biology, how transcription and translation goes in codons, so sets of 3 base pairs. If you take one or take one out or put an extra one, it kind of does a frame shift. Mutation is what we call it. So it offsets, and so they're not in sets of 3 anymore. So that can have huge impacts on which protein is produced at the end. There's also genetic variations that can occur on a bigger level, the chromosome level. You can have translocation, and if you think back to the Philadelphia chromosome, the BCR-ABL translocation is a pretty classic example of that. There can be an inversion, which is just when a section of the chromosome gets flipped around, and you can visualize that done at this last example where the C and B genes have just switched places. And then there's also fusion or fission when an extra piece gets attached onto the end of the chromosome or a little bit falls off. So those are some of the more common examples of genetic variation that can take place that can impact medications. And so specific areas of impact, genetic variation can affect drugs in 2 main categories. You have pharmacokinetics, which is how the body affects the drug, and pharmacodynamics, which is how the drug affects the body. And so in kinetics, you have absorption, distribution, metabolism, excretion. The classic example that you usually think of most commonly with pharmacogenomics is the impact of metabolism. So if you think, if you have a variation in how an enzyme breaks down a medication, if it doesn't break it down as well, then you're going to have increased amount of that drug in your body. But if it breaks it down too much, then that'll be decreased. So that can really affect how much drug is in the body. And then on the pharmacodynamic side, for example, if you have a receptor that has a genetic variation that prevents the drug from binding at the receptor as it usually is intended to, then the drug will not be as effective. So So these are just a couple examples of how variations can affect drug response. All right, so now we'll go into a review question. These will be sprinkled throughout. What is pharmacogenomics? A, how medications affect the genome. B, how the differences in individual genomes affect responses to medications. C, research that uses genomics to discover new drugs. D, how proteins turn genes on and off. Or E, I still don't know. Hopefully you do know by now. Right, so people answered pretty quickly that time. All right, so I want to go just a very brief history of pharmacogenomics. The term was coined in the 1950s when they were doing some studies kind of realizing that genetics could impact responses to medications. For example, there was a study that looked at succinylcholine in patients that had, and they noticed that 60 patients or so had increased or prolonged apnea after taking doses of succinylcholine. They required very small, diminished doses of succinylcholine. And so these patients were correlated with a decreased amount of esterase that broke down the succinylcholine. So then that begs the question, why do some patients have decreased amounts of esterase in their body? And the answer they proposed was genetics. And so it wasn't until later that we were able to actually correlate that to an actual gene. We only completed the human genome project in 2003. But since then, over time, we've only learned more and more. There's more research, more evidence of the genes and how they interact with medications. We have better technology that can sequence faster, more accurately, and becomes cheaper as the market is becoming more competitive. And just in general, we have a much more comprehensive understanding of how genes affect medications. So where are we now? Well, today there are 181 drug labels that the FDA has mandated pharmacogenetics information to be included, and 44 of these are considered to be required testing, and 86 are actionable, meaning that if you did the genetic test for these medications, then you could actually change your practice on how what medications you give the patients. 6 of them are considered to be just recommended testing, and 43 are simply informative. Interestingly, 14 of these labels have dosing information involved, so it kind of gives them more of a specific guideline of what to do in practice. All right, so briefly, where are we in the integration into healthcare? Well, we have a good foundation of research. Again, there's more being published all the time, but we have research, and then we have some translation. People have looked at the research, determined what's most relevant and most clinically applicable, put it into some guidelines, and then we're kind of stuck between translation and application, where it's applied in the practice setting and affects practice. So I'm going to briefly talk about cytochrome P450 just because I'm going to talk about it a lot here in a second. It is a family of genes that code for enzymes that metabolize a huge amount of medications. So their cytochrome P450s are commonly abbreviated as CYP, CYP, and they usually come with a little bit of alphabet soup at the end of their name that verifies their family or whatever. But the important thing is that they code for an enzyme. All right, so now we'll establish a little bit of technology and hang in with me here. I know it looks like alphabet soup, but it'll make sense here in a second. For all intents and purposes for these lectures, pharmacogenomics is going to mean the same thing as pharmacogenetics. I'll use those terms interchangeably. Technically, pharmacogenomics is a bit more broad. It looks at multiple genes and drugs at the same time and how they interact, whereas genetics usually focuses on just one interaction. But again, for here, they're the same thing. Genes have been developed to have a standardized nomenclature through the Hugo Gene Nomenclature Committee, commonly abbreviated as HGNC, so if you see that around. And this standardized nomenclature is used by a lot of the major pharmacogenomics organizations like PharmGKB and OMI, which we'll talk about in a little bit. Difference between genotype and phenotype. Genotype is a set of one's genetics, specifically their genes, whereas phenotype is the observed effect of those particular genes. So you could have a gene that says you're tall, and then your phenotype is that you're tall. Or in this case, we'll be looking a lot at enzymes. You could have a UGT1A1 gene and a UGT1A1 enzyme. So it's kind of confusing that they have the same name, but you can always tell which one's the gene because it'll be italicized. Whereas the enzyme or protein or whatever it is, the product will be normal. So that is, I'll try and clarify when I can which one, if I'm talking about the gene or the enzyme, since they do have the same name. Gene versus an allele. Allele is that little star that we were talking about earlier. It designates what version of a gene somebody has. So someone can have a normal gene, which is usually indicated by a wild type, is what we call normal. Or they can have a different version that has a polymorphism or two in it, or more. And those are usually indicated with a star and then a number other than 1. So they can, and alleles can have different phenotypes. So the star 2 allele could be a poor metabolizer of UGT1A1, or it could be an increased metabolizer depending on which gene you're looking at. And so homozygote versus heterozygote, if you think you get, everyone has 2 alleles of every gene in them. You get 1 allele from your mom, 1 allele from your dad. If they are the same allele, you're considered to be a homozygote. If they're different, then it's considered to be a heterozygote. And so again, just looking at the nomenclature, CYP2D6 star 1, that'd be a homozygote for wild type gene, always indicated with star 1. And then if you're star 1, star 4, you're a heterozygote, or star 2, star 4, anything like that. And then just to reiterate, wild type is always designated by star 1, is considered the average normal arbitrary standard of a gene. And then important to denote here is that any other time an allele has a number designated to it, it does not indicate what functionality it has. It's just merely the order that the alleles were discovered. So star 2 was the first allele discovered after normal, and star 3 was next, etc. It does not necessarily mean that all star 2 alleles are poor metabolizers, for instance. So important to designate that. And hopefully this alphabet soup makes more sense now. And kind of elaborating further on the degrees of enzyme activity, these are also standardized terminology, and they correlate with the degrees of allele function. So if you're a poor metabolizer, that means your enzyme has the least function, and it usually has an allele. You usually have 2 alleles that have decreased function. Whereas an intermediate metabolizer, you might have 1 allele of normal function and 1 allele of decreased function. Normal metabolizer is also called extensive metabolizer, depending on which source you look at. So extensive means normal in this case. I know that can be confusing too. You usually have 2 normal function alleles. Or rapid metabolizer, either 1 increased function allele and 1 normal function allele usually. And then an ultra rapid metabolizer, usually 2 increased function alleles, or a normal allele and a copy number variation of normal allele. And if that was a little confusing, here's a chart that kind of helps break that down, visualize that a little bit more. You have the first allele up here on top, and then the second allele on the side. Here's the different designated activities on each axis. And so if you have 2 null alleles, you're a poor metabolizer. And then, for instance, if you have 2 normal alleles, or 1 normal allele and 1 reduced allele, you can be extensive. I should clarify, null means no activity of the enzyme. Like, it absolutely does nothing. Whereas reduced means it has a little bit of activity, but not a lot. And then if you have multiple copies, you're either extensive or ultra-rapid. All right, so now we can apply what we just learned with the terminology to what we can see in EPIC. So this functionality exists. It's actually there. It's called genomic indicators. If you go down to more activities, and it'll pop up, it'll be there. There probably won't be any information in there because we don't have very many test results for genetic test results for any patients yet. But if there was going to be information on your patients, might be what it would look like. It'll give the gene and what phenotype they are, in this case, a poor metabolizer. It'll give a short description of what this means, as well as a couple of common substrates of that enzyme that might be affected by the altered genotype, and as well gives some common resources that you can go to further look into that. And so this is also something that exists in EPIC, but you've probably never seen before because we don't have test results. This is a best practice alert that will fire if a patient has genetic test results that indicate there are poor metabolizers or extensive metabolizers that might actually cause some severe reactions or lack of reactions to medications. So it'll fire upon ordering a medication if the patient has that test result available, along with some other criteria. So this is an example of what a best practice alert might look like. Example for clopidogrel, it'll be a statement and a suggestion, pretty strongly consider an alternative. More details, and then a couple of alternative medications that you can consider that won't interact with this medication, as well as the opportunity to remove clopidogrel and replace it with one of the alternatives. So this will be a way that you can rest assured that if you don't remember exactly every single thing I talked about in these 6 lectures, when genetics becomes more common in practice, this will be there to help remind you. And then I just want to give you some good resources to go to if you have more questions about this, or if you want to just remember what we talked about. GKB is a really good resource. You can search by medication, you can search by drug, and it'll guide you toward the guidelines that are available. FDA labels, again, have, you saw that 181 drugs have pharmacogenetic information in the labels. They have varying degrees of helpfulness, but it is there. The OMI, which I mentioned earlier, is the Online Mendelian Inheritance in Man website, and that is a good place to go to look into more specifics about genes themselves and their alleles and what they indicate. And then I mentioned you can get to the guidelines from the PharmGKB. Common guidelines include the Clinical Pharmacogenetics Implementation Consortium. This is an international group that looks into research that's coming out all the time about relevant and clinically applicable pharmacogenetic studies, and they translate that information into guidelines. And so we'll be looking at a lot at those over these next 6 lectures, as well as from the Dutch Pharmacogenetics Working Group and the Canadian Pharmacogenetics Network for Drug Safety. So this is just a screenshot of the main PharmGKB page. This is what it looks like. There's this search bar that you can search by driver, gene, or whatever you want, and it'll take you to where you need to go. It's really fun to look at, or at least I think so. I'm not sure if you will. And here's an example of what the CPIC guidelines look like. They come in as kind of standardized form with the phenotype on the left-hand side. You can see either ultra-active metabolizer all the way down to poor metabolizer. The different genotypes, the different alleles that are cause those different phenotypes. Examples of diplotypes, we won't get into that. Implications for what results on a physiological level from that change, as well as recommendations that you can, recommendations of what to do if your patient is one of these phenotypes. So in the case of an ultra-active metabolizer, it just says for clopidogrel and 2C9 team, use what you're already doing, drug label. But if you look down at poor metabolizer, it says use an alternative antiplatelet therapy. And that's strong evidence right there, strong recommendation. So that's what the previous EPIC BPA was about. All right, another quick review. What does the star indicate in SIP 2D6 star 2? A, gene, B, a diplotype, C, a protein, D, an allele, or E, I don't know. I see some confident clickers. I like it. I'll still let it run out of time. All right. I want to briefly discuss medical genomics. This isn't the focus by any means of these studies, but pharmacogenomics is an aspect of medical genomics. Medical genomics is a broad umbrella of anything that relates genomics to health, improving health using genetics. And so, a couple examples of these, trisomy 21 would be an example, or the Philadelphia chromosome again, the BCR-ABL translocation. Any of those like genetic diseases, cancers even, or a couple of instances where it's kind of closely related to pharmacogenomics include UGT1A1, which is an enzyme that metabolizes a lot of drugs, again, a certain allele that can cause Gilbert syndrome. So another medical condition that's